Hi guys, welcome to this week content, which is all about volumetric and gravimetric analysis. Now, volumetric analysis basically is a quantitative analysis. It is actually titrations. What titrations we have done before would be like acid-base titrations, which you have just done it for that report. The back titrations between an acid and a base, antacid tablet and HCl. All right, and then we have gravimetric analysis. Gravimetric analysis basically is a precipitations reactions. We are trying to determine a quantity of an ions in a solutions. Let's say, for example, we have AgCl, silver chloride, right? Silver chloride is a white precipitate. When you mix silver and chlorine together, you will get a white precipitate. So if you have a solution, unknown solutions with chlorides in it, right? So we want you to determine the amount of chloride in the solutions. Now, chloride itself is colorless. Okay, how can we determine the amount of chloride ions in a colorless solutions? We just need to add in silver ions, silver nitrate, for example. And from there, the silver ions will try to react with the chloride, to form white precipitate. Okay, and from the amount of solid form, the precipitate form, we can calculate the amount of chloride from the solution itself. So this is about gravimetric analysis. Now let's look at the learning outcomes. Number one, we must be able to define volumetric analysis and perform volumetric calculations. Basically acid-base titrations, and we do all the mole calculations, right? And next, we must be able to describe and perform calculations for complexometric titrations. Complexometric titrations involve complex ions, which we're going to learn about it in a while. And then the third one will be to describe gravimetric analysis and perform its calculation. So this is what I meant just now, to calculate the amount of precipitate form, and then from there do a backward calculations to get the amount of ions in it. So what is that volumetric analysis? Like I said, a quantitative analysis is involve the measurements of volume of a solutions with known concentrations to determine the concentration of another solution. Now let's say, for example, a titration always with a burette and a conical flask. Okay, so the solutions in the burette is usually the standard solution. Right here, the standard solution, which is the one with the known concentration. That's why we call it as a standard, because we know the concentration. And then in terms of its volume, it depends, right? How much we use to get the endpoint of the titrations. So the one in the conical flask is actually with unknown concentration. This is the one we're calculating, we're determining. All right, unknown concentration, but in terms of volume, it is known. We fix it. Let's say we fix it at 25 centimeter cubic, and that's how we set up our titrations, right? So usually we will use the burette, we drop it in, and then we add in an indicator for the titrations for it to have a visible change at the endpoint, right? So we start dropping in the known concentration. Let's say this is actually an NaOH, and this volume of 25 in the conical flask is actually HCl. We want to determine the concentration of HCl by adding NaOH to neutralize it. So the NaOH will keep adding on until the color of the indicator change. And of course, the color change, it depends on the indicator used. It can be a methyl orange or phenolphthalein. So up to the color change, we stop adding in NaOH, then we read the volume. Okay, we measure the volume used. So let's say the volume used until the color of the indicator change is 30 centimeter cubic, let's say. All right, we have used up to 30 centimeter cubic from the top. Then what happened next is we're going to calculate the mole, 30 centimeter cubic, and the known concentration of NaOH, MV over 1000. You will get the mole, right? So from here, we can calculate the mole. So once we got the mole of NaOH, we're going to compare it with HCl in a balance equation. So we write the equations out, NaOH reacting or neutralizing HCl, and you're getting NaCl plus H2O, right? And then now, this is a balance equations, and we found out that the ratio is 1 to 1. So let's say I have X mole of NaOH, X is here. So what is the number of mole of HCl? Same thing, X mole. Right? Now we got the mole of HCl, and we have the volume of HCl. From here again, sub into the same formula, we can get the molarity, which is the concentration of the HCl. So this is the basic concept of acid-base or a volumetric analysis. Okay, so the main thing is you must have a standard solutions. And how can we prepare a standard solutions? A standard solution is prepared from a primary standard. What is that, a primary standards? These primary standards is a substance that with the following characteristics. Number one, it must have high purity. Okay, no other impurity in it. Why? Because let's say for example I have 3 grams of NaOH, but these 3 grams of NaOH is impure. So that would means I have less than 3 grams of pure NaOH. Am I right? Because within the 3 grams, some portion of it is actually some other compounds. So let's say for example, within the 3 grams, 0.5 gram is impurities. So the actual mass of the pure NaOH is just 2.95, right? 2.95 grams instead of 3 grams. But if we are unsure about the purity, okay, we take 3 grams of NaOH and we try to dissolve in solution of 25 ml and we make a standard solutions. And then from there we know the concentration. But that concentration is actually based on 3 grams. In fact, it is only 2.95 grams. So the concentrations that we calculate is actually higher than expected. So that is why it is inaccurate. So if you have a standard solution that with inaccurate concentration and then you use it to titrate with a HCl, the concentration of HCl obtained will be inaccurate as well. The percentage error will be high. So the compound must have high purity. That's the one thing. Next, I highlighted stable to air and in solution. And why is it must stable to air and in solution? Because when you have a solid state of NaOH, for example, if it is not stable to air, once you open the bottle, it exposed to the air and it start reacting whatever things in the air. And then you continue the process of preparing the standard solution. So the standard solution is no longer NaOH because it might react with the air to form something else, different substance now. So the chemical formula, everything changed before you actually do a titrations. Alright, so that is why it must be stable to air, and as well as in the solutions, it will not react with the solutions. It will not react with the water. And what does that mean by not react with the water? Now, when you put NaOH into water, it will dissolve. That's how we get a solution at the end, standard solutions, right? Now, dissolving a substance in a solution is different from reacting a substance with water. You see that? So reacting meaning that the chemical formula will change once they actually mix with water. Dissolving means the chemical formula remain the same, but the physical state just changed from solid into aqueous. Just that. So only physical change, no chemical formula change. So that is what we call dissolve. But if something that dissolve and then react, the chemical formula change, that is different things. Okay, so that's what we don't want to see, because we want the solution of that compound itself. We are not having a different compounds then. Okay, so it must be stable in air and solutions, and high molar mass. Now this is a bit quite subjective. What does that mean by high molar mass? What is the standard value? Above certain value, then it is considered high molar mass. We don't have a standard value for this, so high molar mass is that's why I say it's a bit subjective. So I'll encourage you guys not to look at it. High molar mass, of course, is not too low. If it is too low, that may actually affect its solubility, or it may be more reactive in the case. So high molar mass is not a good characteristics to look at in order to prepare a primary standards or a standard solutions. But then the last one, readily soluble in water, like I mentioned, it must able to fully dissolve in water. Dissolve, not react. Okay, and why is it so? Because let's say again 3 grams of NaOH, if it is fully dissolved, we base on 3 grams and the volume, we can calculate the concentration. What if you put in 3 grams of NaOH but only 2 grams dissolve, 1 gram remain undissolved, remain a solid? But then we assume that all 3 grams dissolve, and then we calculate the concentration based on 3 grams rather than 2 grams. That will give us an inaccurate value, all right, with high percentage error. So this compound itself must be fully soluble. Okay, it must be fully soluble, otherwise we are unsure about the amount of NaOH dissolved, how many grams actually dissolve in it if it is insoluble, because it's hard to, yes, we can see the precipitate in the beaker, it is remain undissolved, but how many grams there? So that is a bit hard for us to measure, right? So make sure the compound is fully soluble, then only we can use it as a primary standard to prepare a standard solutions. Now, the types of volumetric analysis, we have acid-base titrations, the common one, and then we have complexometric, which I'm going to introduce to you guys something new, and redox titrations. I'm sure you guys heard of it. It's a titration, it's a reaction that is a redox, oxidation reductions, right? It's the same thing like acid-base. It's just in the titration format, burette and conical flask. Okay, acid-base titration, like I explained just now, you will need a standard solutions, you will need an unknown solutions, you will need an indicator. The indicator are commonly weak acid that will change color from one pH to another. They will have a pH range where the indicator will change color. We need a visible change to tell us when to stop adding a standard solution into a conical flask, right? And the color change of the solution, we call that as the endpoint. And then when to stop, that's the point where we need to stop. And this endpoint must coincide with the equivalence point. Again, what is that equivalence point? Now you have a titration curve here. This is the pH value, all right? This is the volume of NaOH. Let's say you are doing a titrations between NaOH and conical flask, right? And a HCl in the conical flask, this is NaOH, this is a HCl. So you're going to drop it in, and then you put in an indicator, the color change. Now, what happened when I start dropping in NaOH? The pH will start from 14 because it's high pH. This is a strong base. And then when you start dropping it into the conical flask, it start neutralizing the HCl, and then the pH will drop up to a certain point. You will have a straight line sharp change here. From 1 pH drop to a very low pH, and then when you keep adding in excess, it will be constant then. So this is the region where we call the equivalence point, and this is where the neutralization takes place. Okay, this is the point actually starting from here when they get a straight line, the vertical line. This is the point where all the HCl in the conical flask has been neutralized. Okay, so now this is not something that we can see. Like, how can we tell the HCl in the solution has been neutralized? Right? We can't see the HCl moving around. So we need an indicator for this. Okay? The indicator is supposed to be there to tell us, yes, that's the point. This is the point where all the HCl has been neutralized. So your indicator must have a pH range that matches this region. So whatever indicator you choose, make sure this indicator can change color, okay, it can change its color at this region, this straight line region, and this straight line region will give you a certain pH value. Let's say from 6 to 8. This is the pH range. It depends on the titrations. Okay, so that's a function of the indicator. And then depends on titration, as in depends on whether you're using a strong acid, weak base, strong base, weak acid, or strong acid, strong base. Right? We learned that. So if it is a strong acid, weak base, the vertical region here, the straight line here, will be above strong acid, weak base, right? Will be below 7 if it is a strong acid, weak base. Now the region will be, let's say, not 6 to 8, but maybe 4 to 6. Example. Okay, that's the equivalence point if it is a strong acid, weak base. But the other way around, if you have a strong base and weak acid, then the range will be above 7. Let's say it is about 7 to 9. That is the point where the indicator should change color. So depends on the titration, depends on the acid base used. You must choose a suitable indicator for that. Okay, let's say for example, phenolphthalein will change color only at the pH above 7. Methyl orange will only change color for the pH below 7. So you must choose the appropriate indicator for that. And let's try an acid-base titration. This is one example. Now there are a few questions here in OL as well. I'm going to show you one type of titrations or volumetric analysis with one example. So this is the first one I'm going to show you. Now a standard solution of sodium carbonate was prepared by dissolving 5.06 grams of anhydrous solute, dry solid, into water and making it up to 500 centimeter cubic. We're going to prepare a standard solution now, obviously. 25 centimeter cubic portions of these solutions were titrated against HCl, giving an average title volume of 19.2. So let's explain about how to prepare a standard solution. At first, you must have a beaker. Now, this beaker, you're going to put in 5.06 grams of sodium carbonate, solid. And then you're going to put it minimum amount of water. And why do we need that? Because we're trying to dissolve it. So that minimum amount of water is something below 500 because we're going to prepare a standard solution of 500, right? So when you use this water to dissolve, we're just dissolving it, all right? So minimum less than that, 100, 200, as long as not more than 500. So, and not close to 500 as well. So let's say we put in 200 centimeter cubic in order to dissolve the 5 grams of sodium carbonate. When all dissolved, we're going to transfer it into a volumetric flask. Now, from the name, it suggests this is for volumetric analysis. We prepare standard solutions. And there is a line here from the flask. This line was stated as 500 centimeter cubic. So this is a standard flask. If you add water up to this line, it means you have 500 ml. Got it? So now what we're going to do is we pour this solution into this volumetric flask. It will definitely less than 500, right? Because we are using 200s. And what next is we're going to add on another 300s. Of course, we are not measuring 300 and pour it in. We just top up with distilled water. By default, all water used they are distilled water. So we top up with distilled water as long as the water meniscus level up to this line. Okay, then you have a total volume of 500. That's it. So we pour the solution in, the one that we dissolved sodium carbonate, and then we just top up with water up to the line, up to the mark line. Then we are having 500 centimeter cubic of standard sodium carbonate solutions. Done. So this is how we prepare a standard solutions. And next thing is we start our titrations. Now they said 25 centimeter cubic of these portions, which means out of 500 that we prepared just now, we take out 25, and these 25 we use a pipette to transfer it into a conical flask. 25 centimeter cubic of diluted sodium carbonate. Why is it diluted? Usually make it clear as in as long as you add water into the compound, we call it as a diluted solutions, right? Okay, now we have this now in a conical flask. How do I know we should transfer it into a conical flask then? Because it gives us 25. So remember what I said? The things with the fixed volume usually in the conical flask. The one with the unknown volume, because it depends on the solutions, right? That will be in the burette, because burette is the one that changing in terms of volume. Conical flask is the one that with unknown concentration. So this is 25 in the conical flask now, and then we are going to titrate it with HCl, because they say hydrochloric acid, and giving you an average title volume. So now the volume of HCl used is actually 19.2. After the titration, they found out that I need 19.2 cm cubic of HCl to neutralize all the sodium carbonate. All right, and next thing, what we're going to do? Equations. Sodium carbonate plus HCl. You're getting sodium chloride plus carbon dioxide gas plus H2O. Right? So then we need to balance the equation 2 NaCl and 2 HCl. So the ratio obviously is 1 to 2. So from here I have 19.2 centimeter cubic of sodium HCl, right? And then we have 25 of sodium carbonate. Now guys, what next? We got the volume, we got the balance equations. Now, do we have the concentration of HCl? No, we are supposed to calculate that. So what do we have here? We have the concentration of sodium carbonate. In fact, how can we do that? Let me show you. Okay, we do the calculations first. Now, I have 5.06 grams of sodium carbonates. I'm going to divide by the molar mass. 5.06 grams of sodium carbonate divided by the molar mass of sodium carbonate. Sodium is 23 times 2, Na2. Carbon 12 plus O3, 48, 106. So I'm going to divide by 106, that's the molar mass. So 5.06 divided by 106, I'm getting 0.048 mole. Okay, so I've got the mole of sodium carbonates. Yeah. Now, this is the mole in 500. Right? This is the mole in 500. And what's the mole in 25? Because we only pipette out 25. In a conical flask, it's only 25 instead of 500, unless we use all of 500. That would be the mole. But now we're using only 25 out of 500. So the mole will be different, right? Obviously. So now what we're going to do is we do the calculation, the ratio thing, to get the mole in 25. So if you have 0.048 in 500, how many in 25? So I'm going to use 25 divided by 500 times 0.048. So then I get 2.4 times 10 to the power negative 3. That's the mole in 25 centimeter cubic of sodium carbonate. So that's what we got. So now we know the mole of sodium carbonate. Let's put it on here. 2.4 times 10 to the power negative 3. So that is the mole of sodium carbonate. And what's the mole of HCl? Based on the balance equation, you need to multiply by 2. Then you get 4.8 times 10 to the power negative 3. So we got the mole of HCl now. And what else do we have? We have the volume of HCl, 19.2. We have the mole, we have the volume, and then we can calculate the concentration. How can we do that? Right? 4.8 mole equals to MV 19.2 over 1000. Then you will get your M value. So answer times 1000, 4.8 times 1000 divided by 19.2, you will get 0.25. So the concentration is 0.25 mole per dm cube. So that's what we have. Okay, so this is the concentration of HCl used. So this is the full calculation for this example. Is everybody clear? Right? So let me know if you need me to revise it again in the tutorial for this part. Right? Let's move on. Now, there are more than one types of questions here. You see that? Vinegar, and then you have this. All answer is given as well as in OL as well. I stated all the answer in. So you can do that again for this acid-base titration. Next, we look at redox titration. Now, what is that redox titration? It's still a titration, but just that it's involved reduction and oxidations. And in this case, right, KMnO4, you see that? Potassium permanganate will always be the common oxidizing agent used. Of course, not only potassium permanganate, K2Cr2O7, potassium dichromate is another type of oxidizing agents that commonly used. So these two, you always see these two in redox titrations, and we don't need an indicator. It says that it's a self-indicator. What is that, a self-indicator? Because potassium manganate is purple in color, and when you titrate it, initially it's colorless, and then when at the end point it turns into permanent pink. Right? It turns from colorless to pink. So as long as there is a visible change, that's good enough. We don't need to add extra indicator. Okay, that will be good, because if we add indicator, in fact, just like the acid-base titration just now, if we add in indicator, we identify the volume already. For purely calculation, that is fine. But what if we need the compound itself? We need the salt that produced from the acid-base. The salt produced is impure because you have indicator in it. And it's very hard for you to separate the indicator from the salt, because both are fully soluble in water, right? So if you have a titration, if you can, without an indicator, that will be good. That is an ideal case. But in this case, redox titration, yes, we can do that, because most of the oxidizing agent that we use are colored. KMnO4 is purple. And what about this K2Cr2O7? It is initially orange. And what is the color change? It will change from orange to green in the titrations. So that's how we take it as a self-indicator. All right? And everything the same, guys. Everything the same. Like in a burette, supposed to be usually standard solutions, and usually. And then in a conical flask with something that we want to determine. And then until we get the endpoint, we calculate the volume, calculate the concentration. Everything the same. That's redox titration. Let's show you another example here. Okay, now. Let's say I have 1.8 grams of iron 2 ammonium sulfate. Formula is given. You see that? Dot 6H2O. This is hydrated. So the solid itself is not fully dried. You have water in it. Okay, anyhow, this was dissolved in 35 centimeter cubic distilled water. and the solution was then diluted to 50 centimeter cubic. See that? They dissolve it first at 35. They try to dissolve 1.8 grams. After that, they further dilute it to prepare a 50 centimeter cubic of the solutions with dilute sulfuric acid. So whatever it is, the total volume now is 50. Okay, next, the final solution was titrated. Now you have 50 with you, titrated against potassium permanganate, and 40 centimeter cubic of these potassium permanganate required to reach the endpoint. What is the endpoint here? From colorless to pink, right? You need 40 centimeter cubic here. So look at that. Calculate the concentration of the potassium permanganate solutions. Now, at the end point, right, all the iron 2 changes into iron 3. So basically, you're changing, first half equation is Fe 2 plus, oxidize into Fe 3 plus plus E. This is what you did in the titrations. That's why you see a color change, right? From colorless to pink. Now, let me explain a little bit on that. Why is it colorless to pink? Look at that. Titrations. Initially, this purple. And why is it not turning purple at the end? Let me explain that. Now, initially, this is Fe 2 plus. All right, you have all the Fe 2 plus in it. In here is the purple solution of KMnO4, potassium permanganate. So now you're dropping in the purple solution. When you drop it in, what happened? This purple solution will react with the Fe 2 plus and changing from 2 plus to 3 plus. So what happened is the color of the solution will change. Okay, the purple solution, drop it in, it will turn into colorless because it reacted with Fe 2 plus. The Fe 2 plus changed to Fe 3 plus, and the manganate, the half equation is MnO4 minus plus 8 hydrogen plus. You have acid inside, that's why we add sulfuric acid, and then the 5 electrons, and then you change it to Mn2 plus. Now this is a colorless compound. This is purple. So based on these equations, right, we can see when manganate reacts with Fe 2 plus, it will change from purple to colorless. So when you drop it in, it turns into colorless. So no color change yet. The color still remain colorless for Fe 2 plus. Now when you keep adding in until no more Fe 2 plus, which means all the Fe 2 plus has been converted into Fe 3 plus, and then you add one extra drop of KMnO4, what happened? Will this KMnO4 or will this MnO4, the purple drop, convert into colorless? No, because there's no more Fe 2 plus. When there is no more Fe 2 plus, the manganate that you added in, the one extra drop of manganate that you added in, will still remain purple. And this purple drop mixed with the colorless solution here, because of volume difference, you only have one drop purple and the rest are all colorless. Then the whole solution will turn into pink, a lighter versions of the purple. That's why it turns into pink. And why is it permanently there as a pink? Because there's no more Fe 2 plus. So we don't expect the purple MnO4 that we added in will turn into colorless because no more reactions. So that is why we know that yes, we should stop now because there is no more Fe 2 plus. See that? So the colorless or the endpoint is changing from colorless to pink by adding KMnO4. So this is how the whole reaction works. Is everybody clear? So yeah, that's what I'm trying to deliver here. Let's continue. Okay, you need 40 centimeter cubic and reach the endpoint. You need to calculate the concentration of potassium manganate. And what we're going to do, step 1 is we're going to use 1.8 grams divided by the molar mass of this whole thing. Okay, so Fe is actually 55.8. Let's add it on. I'm calculating the molar mass. 55.8 plus with ammonium, 2 ammonium, so what is that? 14 plus 4. 14 plus 4, 28. 28 times 2, 56. So plus 56 plus sulfur, 32. Plus 32 again because times 2. Plus with oxygen, 64 times 2. Plus with 6 water. The dot here is plus and not multiply. So you plus with 6 water, so it's 6 times 18 for water. And then you get 411.8. 411.8. That's the molar mass, right? So from here we can get the mass, 1.8 divided by answer. 0.8 divided by answer, you get 1.8 divided by 411.8. You get 4.37 times 10 to the power negative 3. Okay, I hope I calculated right. Just double check. So I've got the mole now. This is the mole of manganate, the purple. No, sorry. This is the mole of the salt, the ammonium sulfate. Sorry. Yep. So that's the salt, the iron 2. Okay, make it as iron 2 then. The iron 2 plus. Okay. Now why am I doing that? Look at that. This formula, right? Imagine if I have 1 mole of this compound, how many iron in it? How many iron 2 plus in it? If I have 1 mole of this compound, you only have 1 iron, right? So 1 mole you have 1 iron. So if you have 4.37 mole of the whole compound, you should have 4.37 mole of iron 2 plus. So that's why I put it as Fe2 plus here. Now, in case you have something like that, guys, just in case. What if you have a formula like this? I have a 2 here then. What happened if you have a 2 here? So the mole here, we need to times 2 because 1 mole of this compound giving us 2 mole of iron. So beware of that. But in this case, right, in these questions, in this particular case, it's just nice, 1 to 1, right? 1 mole of the whole salt. I have 1 mole of iron 2 plus. That is why it can be the same. Right, so I got the mole of Fe2 plus, and then what else can we do? I have the mole now, all right, and then the total volume is 50. That doesn't matter because we are just adding water into it. The mole remain unchanged. When you add water or sulfuric acid, the sulfuric acid is not reacting with it anyway. It's just a catalyst. So now in this case, I have the mole of Fe2 plus from the total volume. Next, we're going to do half equation like just now because we need the mole ratio. So initially Fe2 plus changes into Fe3 plus E. That's the oxidations. And reduction will be the one just now I show you, MnO4 plus 8 hydrogen plus 5 electrons changing into Mn2 plus 4 H2O. So that is the equations, the half equations, the oxidation reductions. And what we're going to do is we balance them. So balance the equations times 5. So we can cancel out 5 electrons, 5. We can cancel out the electrons. And next we're gonna check the ratio. 1 manganate, 5 iron. So ratio is 1 manganate to 5 Fe2 plus. We've got the ratio. And now step 2. Oh, sorry, this is step 2. Step 3. So what we're gonna do? We have the mole of iron, which is 4.37 times 10 to the power of negative 3, and then what is the mole of manganate? Because we need to calculate the concentration of manganate. So from here, we divide by 5. You've got the mole of manganate is 8.7 times 10 to the power of negative 4. So I have the mole of manganate now, and the volume of manganate used is 40 centimeter cubic. So how can we do that? Just calculate the concentration. So 8.7 times 10 to the power of negative 4 equals to mv 40 over 1000, and then you can get your m equals 2. So let's do this times 1000 over 40. You get 0.02. So m equals to 0.022 mole per dm cube. So that is the concentration of the manganate. See that? Overall calculation is still the same as acid base. The only difference is this is a redox titration where we have half equations like that. And then we need to do extra step. We need to combine the half equations in order to get the mole ratio before we can calculate the concentration of the unknown compounds. So this is what we're going to do. Okay, so that's a redox titration, everybody. So next, move on. Of course, we have more than 0.023 about that. Okay, so we have all this example with answer given, so you can try on your own. Next, yes, we should look at complexometric titrations. Okay. Now, this might be something new because in this semester we're going to learn what is that complex ions later, right? Complex ions. But to explain it in a simple way, Again, it is still a titrations between conical flask and burette, right? We put in something here, and then we do an endpoint. So this complexometric titration is involving a complex ions. Now, what I show you on the right hand side of this slide will be all these things. See that? All these NTA, EDTA, DCTA, DTPA, and AGTA. All these are known as ligand or chelating agent. Now, what is that ligand and what is that chelating agent? All these so-called ligands are very sensitive to metal ion. Very sensitive as in they have high affinity towards metal ion. Let's say I will take this EDTA as an example. Okay, do we have yeah, there you go. Let me draw it out instead of showing the diagrams. So see, how does this EDTA has high affinity towards metal ions? Now when you have EDTA like that, let me draw it again. Okay, you have NH, right? Carbon, carbon, and then NH again, and then this is COOH when you dissolve in water. Sorry, it should be COO minus because the COH is a carboxylic acid that it dissociates into ions. And then you have another one which is COO negative as well, COO negative as well, COO negative as well. Oh, my bad. So it should be a CO minus then. Okay, when you put this thing in the aqueous solutions, nitrogen is positively charged because you have 4 bonds with the H in water. So 1 bond, 2 bond, 3 bond, and the H 4 bonds. So when nitrogen having 4 bond is automatically positively charged because of the dative bonds, right? You don't need this lone pair. So this is how it looks like. You have positive and negative in water, right? So now what happened when you put this thing in water? Let's say the solution itself having a copper 2 plus ion in it. So what happened? The negatively charged will be attracted to the positive ion, attracted. So it looks like the COO minus, the 4 COO minus, like a crawl. Okay, like a crawl that grab the copper 2 plus metal ion, because the 4 crawl here are negatively charged and they will attract the copper 2 plus. They will just grab it and hold it with it. So this ligand is like a tongue, like a wooden tongue that you use to grab something up. But in this case, in a chemical form, they use this ligand to grab the metal ions in the solution form. Because in the solution, we can't use a physical tongue to grab it, right? It's an ions, guys. It's too small. We can't see it. So we need a special tool to do that. So what are the special tools that we're using here? Ligands. So in this case, EDTA. When you put EDTA in, automatically this EDTA will grab all the copper ions in it because they are oppositely charged. So this is how they grab it and hold it together with it. Okay. So the grabbing process, we call it as chelating or chelation. That's why instead of ligand, sometimes they call it as chelating agent. They try to chelate it, they try to grab it. So this is how they form a complex ions. So when the EDTA grab the copper 2 plus, this whole thing, when they grab the metal ion, this whole thing, they call it as a complex ion. Why is it a complex ion? Because it's complex, right? It's too complicated. It's so complex in it. And then grab the copper ions, and it's ions, so complex ions. So this is what we call a complex ions. And how can we apply this in the titrations? Look at that. By the way, you don't need to remember all the complex. The ligand is given, right? Let's see this. Example, I have copper 2 plus in a solution. I try to remove this. I try to remove all the copper 2 plus because copper is a heavy metal and it's toxic to the human body, right? So let's say you have small amount of copper in a water, drinking water. We will not drink it even though it's small amount, right? Because it's toxic to our body. We put in some EDTA into it, and this EDTA will grab the copper and we try to filter it later. Okay, we try to remove the copper, and that's how we applied it in the titrations. Now look at that. I have copper 2 plus and I have free indicator, purple. We have the free indicator. So what happened is when you have an free indicator, initially was purple, reacts with copper 2 plus, you will get a metal ion indicator complex. It turns into yellow. So initially copper with low concentration, I know you're asking why not copper is blue, right? So when copper at high concentration, yes, we can see the solution as blue. But if it is at trace amount, low concentration, we will see it as a colorless solution, no different. Okay, so now we mix the copper solution, with copper with this indicator, free indicator, then it will turn into a yellow solutions. And this yellow solution is going to further react with the EDTA, the example that I give you just now, the ligand. And this ligand will grab the copper away to it. So when they grab it away, the yellow color will change into colorless and you free up the purple ions. So basically in this whole process, right, first we combine the copper with the purple indicator, turn it into yellow, and then we titrate it with EDTA, changing from yellow back into purple. So when they're back into purple, from this whole process, we can identify the amount of copper ions in it. Let me explain in a more detailed form. So yeah, oops, sorry. So yeah, initially, I'm going to mix this and these together in a conical flask. So when I mix them, you will get a yellow solution here. All right, yellow. And now in the burette, I'm going to titrate it. Inside is actually the EDTA. It is colorless initially, colorless. And then we drop it in. And this thing will start combining with the copper, right? Because EDTA is strongly affinity to the copper. They will grab the copper away. So when they grab it away to the EDTA to form this, they will change from yellow into purple. So when the yellow solution turns into purple, that is the endpoint. That is when we need to stop. So the amount of EDTA used, let's say, I've used up 25 centimeter cubic and the concentration is 0.1 mole per dm cube, let's say. So from here we can calculate the mole. Let's do this. 25 times 0.1 divided by 1000, you get 2.5. Mole equals to 2.5 times 10 to the power of -3. So I have 2.5 times 10 to the power of -3 moles used. And so what is the mole of this yellow solution? The ratio is 1 to 1. So same thing, 2.5 times 10 to the power of -3. Oh, sorry. Right? 2.5. So if we have 2.5, which is this, right? Just now, same thing. I just put it into this equation. So 2.5 times 10 to the power of -3. So from here, can you get the mole of copper in the solution initially? Same thing, 1 mole to 1 mole. So yes, the copper ion is 2.5 times 10 to the power of -3. See that? From this process, I've got the mole of copper ions. And from there, if I have the volume of the copper solutions, I can calculate the concentration. So that is the reason why we need to do a titration like that. So the overall purpose is to make use of EDTA to react with the copper in order to determine the mole and the concentration of copper ions in an unknown solution. So this is what we call a complexometric titration, because in the process, we are forming a complex ions of EDTA and metal. This is a complex ion. That's why they call it as complexometric titrations. Hope you can get that. And since we put in the indicator that they will change a yellow into purple in the whole process, yeah, as long as there is a color change, we can do a volumetric titrations or volumetric analysis. Okay, so this is complexometric, and then I'm going to show you one of the example. Okay, this one. Okay, let's see. Now, calculate the concentrations of zinc sulfate solutions from the following data. 25 centimeter cubic of solutions zinc sulfate when added to alkaline buffer and Eurochrome black tea indicator. So doesn't matter as long as you know it's an indicator to have a color change. Required 22.3 centimeter cubic of 1.05 times 10 to the power -2 mole per dm cube of EDTA solutions. The equations for the reactions can be represented as this. Now, they want the concentration of zinc sulfate, which is this. Okay, and from the whatever given in the questions, what do we have? We have the volume of the EDTA and the concentration of the EDTA. So from here, I can calculate the mole. 22.3, all right, multiplied with 1.05 times 10 to the power of -2. So that's the concentration volume. Divide by 1000, I can get the mole. So 1.05 times 10 to the power negative 2. Very good. And then multiply with 22.3 divided by 1000, you get 2.34 times 10 to the power negative 4. So that's the mole of ETT used for complete reactions, right? It's very simple. And what's the mole of zinc then? So ratio is 1 to 1. Now, give you a hint here. Complexometric titrations with ligand, right? It's always 1 to 1 unless stated otherwise. Usually it is 1 to 1 because one ligand will actually grab one copper ions or whatever metal ions it is. So always remember it's just one. Strong gripping, but it's just 1 to 1. So then the mole of zinc here will be the same. 2.34 times 10 to the power negative 4. Right? Now you've got the mole of zinc. And what is the volume of zinc sulfate? 25 centimeter cubic. So 2.34 times 10 to the power negative 4 equals to mv 25 over 1000. And from here, you can get the concentration of zinc or zinc sulfate, right? So let's try it out. 2.34 times 1000 over 25. Yes, you get the concentration 9.37 times 10 to the power negative 3. So this is mole per dm cube. That's the concentration of zinc 2 plus ions. But is it the same as zinc sulfate? Let's check it out. Right? Is it the same as zinc sulfate? Let me erase this first. So what we are calculating here is actually for zinc ions, right? Because in the equation is zinc ions. So now we have concentration is 9.37 times 10 to the power negative 3 mole per dm cube of zinc 2 plus ions. Is it the same as zinc sulfate? Let's check. Zinc sulfate is ZnSO4. When you dissociate, you get zinc 2 plus and sulfate ions. See that? Ratio of zinc sulfate to zinc ion is 1 to 1. So if the concentration is 9.37 here, the concentration of zinc sulfate overall is the same, 9.37 times 10 to the power negative 3. You get it? So that is your answer then. Okay, so this is how we do a complexometric titration here. All right, 9.37. See that? That's the answer. The rest you can try it out yourself. Now back titrations, I guess no further introduction on that because you have done the lab reports, I guess, by now. So this is a back titrations reactions. I'm going to skip it, right, because you have done it. So this is one type of titrations, but then we are not doing it directly. You get what I mean, right? So I'm sure you're better than me now after that you have done complete the lab reports. Let me know if you need help in any way of that. Now, last one, gravimetric analysis. Like I said, gravimetric analysis is a process of determining a certain compound or certain ions, the concentration of certain things in the solutions where it is invisible, so we can't see that. But we need to add on something else into it to precipitate it out. So they saw it as process of precipitations. We're trying to form solid in this gravimetric analysis. Okay, let me give you an example here. In this slide, right, they give an example of what? Of forming this. Look, solid soluble salt containing iron and other chemical species. So we have iron 2 plus in it. Now they are soluble, right? Dissolve in water. Solution with dissolved iron and other chemical species. Doesn't matter what is that other chemical species as long as we know iron is there. So no iron. Lead is there. Pb is there. So we have lead ions in the solution and they dissolve in water. Okay. So obviously it's colorless, right? So how can we determine the amount of or the concentration or the mole of Pb2 plus in the solutions? We just need to add in another reagent where they can precipitate the lead out. So what combined with lead, Pb, you will give a precipitate, sulfate. Because Pb 2 plus any sulfate ions, you are getting lead sulfate, which is a white precipitate, solid. So from there we can pull the ion, the Pb2 plus into a solid from ions, right? Because in ionic form we can't see anything. So now that's why in step 2, right, we add any solution with sulfate ions into it. So when you put it in and you keep stirring it, you can see a lot of solid form. See that? This is a solid. When Pb2 plus react with the sulfate added, they start precipitating and you get a lot of solid. After you get a solid, we do these things. What do we call this? This is not a normal filtration. This is what we call a suction filtrations. Now, what is that suction filtration? It's much better than the normal filtration. Still remember, the normal filtration, we will only use a filter funnel, conical flask or beaker, and then filter paper in it, and then you pour the solution in. The solution will slowly drip it out, the filtrate, right? And then the residue here is the solid. And this process takes forever because it's using gravitational force, right? It allows it to slowly drip in, and then only you get a solid. And the solid, the residue that you get on the filter paper is not fully dried. You have to put it in the oven and make it dry, right? It takes a longer time. But if you have a suction filtration here, see that? This part is actually a suction that going into a vacuum pump. So this part will be a vacuum now once you're on the pump. And when there's a vacuum, they will suck the air in from the outside. So imagine you pour your solution in here with the filter paper in it. When you pour the solution in and you're on the suction pump, they will suck all the solution down instantly into this conical flask. When they suck all the solution down, all the water in, the solid, the residue on top of the filter paper will stay there, and it is rather dry already. If you leave it on for a few minutes, the solid itself is dried because they keep sucking the air and they will suck all the water residue from the solid. The solid on top of this filter paper is dry. So you need not put it into the oven. Maybe yes, you just put it in the oven for a shorter time. Then you can weigh it. So this is suction filtrations. It's very useful. And next, once we got the solid, what are we going to do? Let's say the solid is dry now. We're going to weigh it. So this is the filter paper with the solid on. And then we put it on the weighing balance. Let's say 3 grams. So we've got it as a 3-gram solid. This 3 gram is actually for PbSO4, right? The white precipitate. And from the 3 grams, we divide by the molar mass of PbSO4. I hope you are following what I'm doing. Lead is 207. I'm calculating the molar mass, 207 plus 32. Sulfur plus 0464, then you get 303. So I'm going to divide it with 303 because this is what we get from the solid form. And then you will get 3 over answer, you get 9.9. 9.9 times 10 to the power -3. So this is the mole of lead sulfate. You see that? And what is the mole of lead? PbSO4, we have to write the equations. We have to split them into ions and see whether it's 1 to 1. Pb2 plus SO4. Yes, it is 1 to 1, right? 1 to 1. So if you have 9.9 times 10 to the power -3 here, you should have 9.9 times 10 to the power -3 here. So you have 9.9 times 10 to the power -3 mole of ions. So from here, what is the concentration of the lead ion initially here in step 1? Because we are assuming that all the ion, all the Pb2 plus presence in the solutions here, all precipitate out as a solid. Everything. Okay? Of course, there are some mass loss in between, you know. We can't actually ensure that 100% precipitate out. Depends on how many sulfate you add in. The sulfate here that you add in should be in excess so that it can pull out as many Pb ions as possible, lead ions as possible. So from here we got the mole, and then we can calculate the concentration. Or we can calculate the amount, which is mole here, 9.9 times 10 to the power -3 moles. So from mole you can calculate, you can convert it into mass, you can convert it into concentration, right? Let's say I want to convert it into mass. So if I have 9.9 times 10 to the power -3 moles of lead, what is the mass of lead ions in it? So we're going to times it with the molar mass, which is lead itself, 207. 2.05 grams. So in total, you have 2.05 grams of lead ions initially from the beginning. So that's how we determine it. See that? Initially, it's an ionic form. We can't even see it. But through this gravimetric process, through this precipitation process, we got to know we have 2.05 grams of lead initially in the solutions. See that? So this process is standard. And for your information, this is what we're going to do for our second lab report. You got that? So yeah, that's how we do gravimetric analysis. I already show you the whole process, right? I mean the calculation. So I'm not going to show you any calculation later, but in OL, try to solve it. Answer is given. Go ahead and do that, and let me know if you need help on that. Okay. So these are the gravimetric analysis things. All the example answer is all given anyway. Okay. See that? All answers given, same as OL. So yeah, thank you guys for this. That's it for the video today for summary for this week, and I'll see you in the tutorial sessions. Thank you guys.